Alright, good day students. So this is week 2, lecture 2, and just to start off as we usually does, there's a positive statement for the day. It's never a situation, there is never a situation or person that you cannot learn something from. So whether it's good or bad, there's always something you can learn from a situation. Alright, so let's recap what we did yesterday. So we defined the average velocity as the displacement over the change in time we have over here, and then also the instantaneous velocity as the limit of the average velocity, as in the limit as delta t goes to 0. So as the change in time goes to 0, it becomes very, very small. Now so I've decided to put this in the slides, the definition formula sheet. So we have these three definitions already. So we have the definition for the displacement, so that's the final velocity minus the initial velocity, or the initial position minus the final position, the average velocity, which is displacement over the change in time, and then the instantaneous velocity, please note the signs here, as the limit of the change in time going to 0. So let's remind ourselves exactly what does the instantaneous velocity mean. So if we have this position versus time graph, and we choose two spots on it, two random positions, and we draw a line through them. So then we have some final position and some initial position along this position curve, and that gives us a change, a displacement, a change in position, and also a change in the time interval, with the final time, the initial time, the final position, the initial position. Now, if we were to choose another point, so let's see what the instantaneous velocity is. We take the limit of delta t, so we make this smaller. So then we choose another point which is closer, so we keep the green line there, but we move this point closer on this curve. So then the displacement becomes smaller as we're moving closer, but the time interval, the change in time, also becomes smaller. Now, and this is the line we get through this point, this purple line. So let's keep that line, let's keep them in green, and then we choose another point, which is a little bit closer. So even that gives you a smaller displacement, as well as a smaller change in time. And once again, we have the purple line. Now we can keep on doing this. So we change that line, that was the line that we had, so we change that to green, and we bring the purple point even closer to this line. And we can keep on doing this. So now the displacement interval is going to be even closer, and we can keep on doing this till we end up with this line. And that is actually the tangent line to the position over here. So what we had at this point is here we move the second purple dot so close to that position, they're basically, wrong way, sorry. So they're basically sitting on top of each other. So we cannot distinguish between those two dots anymore. And that's when you have the tangent line. So it's not that they are infinitely close together, but they are very close together. That the delta t is not exactly 0, but it's striving towards 0. So then you have this tangent line to the curve at that position. And this would give us the instantaneous velocity. So from this, we can infer that the change in the displacement over the change in time is the slope of the graph if we're looking at the position versus time graph. And then since the average velocity is just this quantity, it's directly related to the slope and the distance traveled. And that makes sense, yes, because the longer the time interval, the further you are going to travel, given that you have the same average velocity. Because if we just take that across, it's velocity times time will give you the distance. That doesn't make sense. Think about it a little more. Okay, but then we look at the instantaneous velocity. Now recapping, that's the limit. So then this instantaneous velocity becomes the limit of the average velocity, and therefore that becomes a tangent to the line as we shown over here when we went through all of this. So then we get the tangent line. So that is the instantaneous velocity. So when we look on this, as the instantaneous velocity on a graph, it is the slope of the line tangent to the position versus time graph, and that's defined to be the instantaneous velocity in time. Now the instantaneous speed, so that's the speed you're traveling at this moment, which is actually what your speedometer in the car is measuring, that is defined as the magnitude of the instantaneous velocity. So this is a good point to make a note. So the tangent line, it's the one that is, so if you were, that only touches the line at one point, and we assume that the line perpendicular to that is perpendicular to the slope at that particular point. That's the definition of the tangent. If you don't know what the tangent, if you forgot what the tangent is, go recap it, read it up on Wikipedia, look it up. So now we're looking at the instantaneous velocity and the instantaneous speed. Now we already said in the previous slide, so that the instantaneous speed is defined as the magnitude of the instantaneous velocity. So the magnitude, once again, the magnitude. So that's because your instantaneous velocity, like your average velocity, is a vector. So it's got as a vector, it's got a direction, a size and a direction. So a magnitude and a direction. So in this case, what we have is that in general, for one-dimensional motion, we've got the instantaneous velocity is plus or minus the magnitude of the instantaneous velocity, because there's no vector there. So this is, you can remember, this is the absolute value of the vector quantity, and that's also plus or minus, depending on the direction, the speed, where S we define as the instantaneous speed. And at this point, you must be able to describe this mathematically. I know, in other words, know the mathematical definitions of what the instantaneous velocity, the instantaneous speed, the average velocity, and the displacement. Know these things. Okay. Next, we're going to talk about uniform motion. Now, uniform motion is defined as motion with a constant velocity. And that is literally straight line motion. And you should think about why. Because remember, what is velocity? If the velocity is constant, the vector quantity, velocity, is constant, which means that it doesn't change in any of those two vector properties. So therefore, it literally comes down to a straight line with a constant velocity and therefore also a constant speed. So it's a straight line motion in which equal displacement occurs during any successive equal time intervals. Any successive equal time intervals. That's called uniform motion. So you're covering the same displacement for the same time interval. And once again, for uniform motion, the velocity is constant, and therefore also the speed, which is the magnitude of the velocity, is constant. So it's a simple case. That's what it is. It's a simple case of what we want to look at. Alright, so this is a graph of uniform motion. Now, how do we know that this is uniform motion? So what do we have on the graph? We have the position on the x-axis, on the y-axis, so this is position versus time, the position vector, and that's in meters. And on the x-axis, we have the time in seconds. And the uniform motion graph defines a straight line. Now, how do we know that this is uniform? So we choose 2 points on the graph, some final and some initial point, which is denoted by the x-coordinate of the time, and its y-coordinate is the displacement, or the position. Sorry, this is the position, it's not the displacement. Same with the initial. Time and position. And then we can work out the displacement, so the difference, the final minus the initial, as well as the time interval, so the change in time. So the final time minus the initial time, let's give us that interval. And the average velocity, if we use this definition, so the average velocity, that's the one with the bar on top, there is no arrow there, that is defined as the average velocity. That is the change in position over the change in time. So final minus initial position, final minus initial time. And from the graph, so when you read off, so final position is 8 meters plus 8 meters, but I didn't write explicitly there because it's position and vector. and the initial position was 4, so plus 4 meters from our 0 that we mentioned, the reference point. So it's 8 minus 4 meters over 20 minus 10 seconds, because the final time is 20 and the initial is 10. That will give you, if you work it out, 0.4 meters per second. And it's implicit that it is positive here. So you don't, if it is, I mean, this is the velocity, so you don't have to write the plus there, but it would be good if you would have put in a plus here just to show that you know exactly that it is in the positive direction. And this is then also the instantaneous velocity. Why? Because it's a straight line, and the tangent to a straight line is just the line. So once again, you can see the instantaneous velocity would not change. So as we make this time interval smaller and smaller, this point would just shift closer and closer to this point. So the tangent at any point of this line is exactly just the line itself. So in this case, for uniform motion, what we can say is that the average velocity is equal to the instantaneous velocity. And what does that velocity look like? So once again, if this is for uniform motion, this would be true for any time because it's constant, like we said in the previous slide. So just go back. Uniform motion has got a constant velocity, so therefore the average velocity is equal to the instantaneous velocity for any time. So if you were to graph this, so this is now a graph of the velocity versus time, this is what it would look like. And this is from our answer on the previous slide. So it's just 0.4 meters per second, which we worked out over here. And that's exactly the slope of this graph. So this is something that's important that you should be able to do. So if I were to give you a position versus time graph, you should be able to interpret this graph so that you can draw the corresponding velocity versus time graph. Now it's clear for uniform motion, it's clear that the slope doesn't change, so therefore the velocity doesn't change. So from this we can infer that if you have a position versus time graph, that when it's a straight line, then it is uniform motion. Because if it's a straight line, the average velocity is just the instantaneous velocity, which is the definition of uniform motion. So you should be able to draw these kind of graphs for any pretty much position versus time graph that I give you. All right. Now, what do we need to happen for this line not to have a straight line graph? So basically, because we can all sorts of straight line graphs, but now we're looking at velocity versus time. So what distinguish A, B, and C? So go think about that. Go work it out. See if you can draw the position versus time graphs of all 4 of these and see what they look like. Would they still be a straight line like for uniform motion? No, it would be not, because here your velocity is for all 4 graphs is 1.4 meters per second. And then as you go to 10 seconds, the velocity is very different for all of them. I mean, this guy doesn't even reach it. It only reached the 10 seconds way over here. So in this case, the velocity stays constant. Here it is decreasing, here it's rapidly decreasing, and here it is very rapidly decreasing. So what happens here? So the same thing you can ask if you were to draw another graph over your uniform motion graph. So what happens between each of these sections? You should be able to interpret it. So we just said that, so this is uniform motion, clearly. Then something happens to the velocity because it goes from 1.4 meters per second to 1.3 meters per second. Then we have uniform motion again. Why? Because the velocity doesn't change for this interval. So the average velocity over this interval is equal to the instantaneous velocity on the interval. Then something else again, and the velocity increases, and there we have uniform motion again, but at a different velocity, obviously. So what's the trick here? So how do you change velocity? That's basically what it comes down to, and that is through some acceleration. Now, changing velocity means that acceleration is present. Now, the velocity vector, once again, velocity is a vector, so it's got a magnitude and a direction. So in terms of an acceleration, this means that the magnitude and or the direction of the velocity can change. It could be either, it could be both. Well, sorry, either and both is the same thing. So it could be one or it could be both. And the average acceleration, once again we're dealing with an average acceleration, is the rate of change of the velocity. So we define it once again in a very similar way that we define the velocity. The velocity we define as a change in the position, and now the acceleration we define as a change in the velocity. So your average velocity is once again defined as a change in the instantaneous velocity over time. So the final velocity minus the initial velocity over the time interval. And once again, the units are in meters per second squared for an acceleration, because there's an additional time here, because velocity is already in meters per second, and now we're dividing by another second. So, excuse me, you need to add your times, so it's meters over second over second. So that's meter over second squared. That's the correct unit over here. So we should add this to our definition formula sheet. So here once again, sorry, I could leave that one out because we have it over here. But we've got the displacement, the average velocity, the instantaneous velocity, and now the average acceleration. So you can pretty much guess that because we had an average velocity here and we defined instantaneous velocity, that at one stage, here we have an average acceleration, that we're going to be defining an instantaneous acceleration as well. And your guess could be that it's very much in pretty much the same way. Alright, now the sign of the velocity, the acceleration of velocity, is quite important. And it's important to understand this conceptually. So when the object's velocity and acceleration are in the same direction, whether it's positive or negative, then the speed of the object increases with time. So let's break that down a little bit. So what are we talking about? We're talking about speed. So the speed is the magnitude of the velocity. That's something we measure also in meters per second, but it's independent of the direction. Now in this case, so here we have the object's velocity and acceleration in the same direction. So therefore it is accelerating in the direction that it is already going. So therefore you can think about it as a positive acceleration because you are increasing the speed. And let's just talk about speed for the moment. We can get to velocity and how you increase that. And when the object's velocity and acceleration are in opposite direction, the speed of the object decreases over time. So now if I'm going forward, but I'm accelerating backwards, that's pretty much braking. So that's what happens if you press the brake pedal on the car, because you're going forward at some velocity and you want to change that velocity, you want to go slower, so then you need to accelerate in the opposite direction than which you are going. So therefore your speed decreases with the time, and this time it has to be the time that the acceleration is applied. If this acceleration is not applied, then it can pretty much be no change in the speed. It's only when you apply the acceleration that there is a decrease, that this decrease or the increase up here would happen. So let's talk about negative acceleration. So negative acceleration, that doesn't necessarily mean that the object is slowing down. Because if the acceleration and the velocity are both negative, then the object is speeding up. So it's not So whether you're speeding up or slowing down is not just dependent on the fact that it's negative or positive acceleration. It is dependent on the orientation of the acceleration with regards to the velocity. So I would rather not talk about deceleration, which means a decrease in speed. A deceleration doesn't directly correlate to a negative acceleration. It would only a negative acceleration would only cause a deceleration if the velocity is in the positive direction and the acceleration is in a negative direction. So I would rather steer clear from using this in the physics course. Just say that if you want to mean that something is slowing down, you say that the acceleration is in the opposite direction of the velocity. And please be clear on this. So this is a good point to make a note and make sure that you understand what's going on. All right. And now we can also think about the sign of the acceleration and the velocity, because in the previous slides we spoke about speed. Now, and how the relative sign between acceleration and the velocity. Now, is there a type of motion that is happening when you have a non-zero acceleration? So there is an acceleration, but your speed does not change. So here we've got the speed. This is the magnitude of the velocity vectors. So can you have a non-zero acceleration, but the speed does not change? And the answer is yes. Because, why? Because we're talking about vectors here. So we have an acceleration. If there is a non-zero acceleration, the vector must change. That is always true. But that does not necessarily mean that the magnitude of the vector must also change. It can either be the magnitude or the direction. So you could have a situation where the speed or the magnitude of the velocity is not changing, but the direction of the velocity is constantly changing. What is that? Circular motion. Because the velocity in this case actually tangential to the curve on which it's moving. And we've showed that the instantaneous, so we're talking about the instantaneous velocity. So if you've got circular motion, then the instantaneous velocity is the tangent to the displacement or the change in position. So that's pretty much just the circle around which you're moving, because that's how your position is going to change. And the tangent to the circle is always changing. Over here, so over there it's pointing straight up. If we're going anti-clockwise, so over here it's pointing straight up. Over here it's pointing straight to the left. Over here it's pointing straight down. Over here it's pointing straight to the right. So even though, because this is a rigid object, so therefore these things cannot be traveling at different speed, otherwise the wheel would break and we'll never have a circus again, because people would die if this wheel break apart. So the speed is constant, but for the motion to take place, the velocity is always changing, because it's the direction of the velocity vector that is changing. So please make a note, go read up about this. This is quite an important concept. All right. So like I alluded to previously, the same way we define the instantaneous velocity, we're going to define the instantaneous acceleration. So it's a limit of the average acceleration as the time interval goes to 0. So once again, here you have the average acceleration, if you remember the definition correctly. Otherwise, just go a couple of slides back. And once again, we're taking the limit, because the acceleration is the change in velocity of the change in time, and now we're taking the limit of this time interval to goes to 0. So when your instantaneous velocity does not change, the acceleration is called uniform acceleration. So therefore, once again, your instantaneous velocity equal to your average velocity. That's when we have uniform acceleration. Uniform motion was when the velocity was equal to the average velocity, but now we're talking about uniform acceleration. And a very good example of uniform acceleration is gravitational acceleration due to gravity. And we're going to be dealing with a lot of that in the future. So here is a graphical interpretation of acceleration. Now you would remember this curve, we had it previously, but then we had it as a function of displacement. Now we have it as a function of velocity versus time. So here, once again, your velocity increases from 20 meters per second to 40 meters per second, and you have a positive average velocity because there's a positive change in the velocity. Here, even though you had to travel at speed, the speed varied. Here the speed is very close to where you started with. So here the average acceleration is quite small. It's close to zero. It's close to uniform acceleration which would just be a straight line. If you understand why I'm saying uniform acceleration would be a straight line, just refer back to what we spoke about for uniform motion. So here there was very little net acceleration, because once again velocity is a vector, so there's very little net acceleration from point A to point C. Now from point A to point D, the velocity actually decreased, because we started at 20, so now we at minus 5 meters per second. So the average velocity was negative because the velocity had to change from a positive quantity to a negative quantity, so the sign was in opposite direction. And then as the velocity further decreases, it shows you that acceleration becomes even larger in the negative direction. So once again, the graphical interpretation of acceleration is the average acceleration is the slope of the line connecting the initial and final velocities on the velocity versus time graph. So the same thing that we had with position and time, which gave us the velocity. So it's exactly the same thing, but now, it's always when you see a graph and you need to interpret this, make sure you know what's on the axis. So in this case, we are speaking about the velocity and the time. And the instantaneous acceleration is the slope of the tangent, once again the tangent, by exactly the same way that we proved for the instantaneous velocity, to the curve of the velocity time graph. So the instantaneous acceleration is the tangent to the velocity time graph. So just to summarize, this is just a summary of the motion diagram. So here we have a velocity pointing to the right, and the arrow has got the same size. So this is uniform motion because the average velocity is equal to the instantaneous velocity. So there's no acceleration. Now there must be some acceleration because the arrow is growing as you're moving in that direction. So the acceleration, but the velocity is ever growing, but in this case the acceleration is constant. So this car has a constant acceleration, so this is uniform acceleration. When uniform acceleration, the velocity is ever increasing because you're keeping the petrol down. I'm sorry it's raining right now, so I hope that doesn't influence the video too much and you can pick up the sound good enough. And in this case, you've got the velocity vector, pointing to the right, but the acceleration vector pointing to the left. So therefore, the velocity is going to change because one, there's acceleration, but the speed is going to decrease because the sign of the velocity vector and the acceleration vector are in opposite directions. So you should be able to generally understand this and to be able to interpret this. And I think I'll end off through there. Like I said, I hope the rain didn't mess up the video too much.